Welcome, AP Chemistry folk. We're here today to go over our lesson for AP Week 7A. I want you to notice that I did put some notes for kinetics there. You can go through those. I'm going to go over some of that in the instruction for today. I've also went over that in live instruction, but those are good things to at least look through and be aware that they are there for your help. And you can take notes on those if you would like. Okay, so let's look at some example problems. So on number one, I asked you to write the rate of the reaction in terms of the change in concentration of each of the reactants and products. This is something that we went over in class, and so we should be able to do that. So as an example, we'll use this equation here. And notice that we have Cl2 plus 3F2 gives us 2ClF3. And so when we write a rate expression, we said that it was important to relate rate, which is the change in concentration with regard to the change in time, with the coefficients in the equation. And this will also make sure that the rate of each of the reactants and products are equal. And we'll see that as we move forward. So rate, if we write the rate expression, we're going to say rate is equal to the change in concentration of Cl2 with regard to the change in time. And notice I must now put a negative sign here because Cl2 is a reactant. And the change in the concentration of Cl2, and this is what your notes say, is actually the concentration of Cl2 at the let's say final, and it says T2 in your notes, minus the concentration of Cl2 initially. So if you, and then we can say by the change in time, or actually let's get rid of that. Let's say Tf minus Ti. So if we look at this, we would see at the end of the reaction, this is final, our concentration would be lower. Our concentration would be lower than our initial. And our time, obviously, would be higher than our initial. So time, you can't have a negative time. So for instance, let's just make this real simple. Let's say that we had an initial concentration of 2 molar, right? And so what we would, and then the final concentration was 1. So what we would say is 1 minus 2. And let's say that it took, let's just say that it took 1 second just to make this as easy as possible. What we would end up with is negative 1 molar per 1 second. And so our rate would actually be equal to, see how the negatives cancel? 1 molar per second. And that's because you can't have a negative rate. And so having that negative sign in your expression helps make sure that the rate is positive. All right. And so that's why we have a negative sign in our expressions, because it's a reactant and that the concentration is going to decrease as the reaction takes place. And so when we say change, what we're saying is the concentration at the end minus the concentration at the beginning. Okay, and if it's a reactant, that concentration is going to be negative. And so if that change in concentration is going to be negative, we have to put a negative in our rate expression so that the rate will end up being positive. Okay, so let us then carry on with this. So I got rid of that example. We now know what the change means. I'm not asking you to break down any times or initial concentrations, final concentrations. Not asking you to do that at this time. So, but what I am asking is for you to determine the rate. All right, I'm asking you to determine the rate expression. So we figured out for Cl2 of all the reactants and products. And so we figured out that for Cl2. Now we know what that little delta means. We know exactly what it means. So let's go on to F2, and it is negative because it's in a reactant, 1/3, and we always use the inverse of the coefficient, so negative 1/3, the change in concentration of F2 divided by the change in time, which is also equal to, now this is positive 1/2 change in concentration of ClF3 divided by the change in time. And so all of these are equal expressions. They're all equal. Now, if we want to determine the rate, all right, and this is what I suggest finding first on this is rate. And I ask you this problem first. This is what problem number 2 asks you about what is the rate of the overall reaction. What I do is I give you the change in concentration of one of the compounds, one of the reactants, and then I ask you what is the overall rate. Well, you can set these things equal very easily. So what you're going to do, and you have to do this, is you're going to plug in. So let's calculate rate. So rate, I don't have any information here. I don't have any information here, but this was given to me. So just like you were given something in your problem number 2. So I'm going to plug this into my rate expression for Cl2. And my rate expression for Cl2 is negative the change in concentration of Cl2 divided by the change in time. So what does that look like? Well, it is negative. What is my change in concentration? It is negative 0.012 molar. And what was my time? 1 second. And so what we see here is that these negative signs actually cancel, and that my rate, I don't need a calculator for this, actually becomes 0.012 molar per second, because rate cannot be a negative value. All right. And so I will tell you this, that determining the rate from a reactant or any compound that has a coefficient of 1 is really easy. All you do is use the same magnitude. But rate must be a positive sign. So notice they both have a magnitude of 0.012. The change in concentration of Cl2 is negative because it is actually decreasing with time, but the rate is always going to be a positive value. You can't say that I went negative 5 miles per hour. It's not possible. And you can't say you went negative on a rate either. Okay, so when we're talking about chemical kinetics, it doesn't make any sense either. So what we would say is the rate of disappearance of concentration of Cl2 is 0.012 molar per second. So the negative sign just means that the concentration of Cl2 is decreasing with time. All right, but the rate is positive value. All right, so now we go and we can use, all of these are equal because rate, which is 0.012 molar per second, is equal to everything. All right, and anyway, every one of these things are equal to one another. We could do this a million different ways, but I always like to solve for rate first. And then once I solve for rate, everything else is easy. All right, and so now we want to figure out how to calculate the change in the concentration of F2 with the change in time. All right, so if we want to calculate the change in the concentration of F2 with regard to the change in time, we just set that equal to rate. All right, do we know the rate? Yes, we do. We just calculated. So we know, and actually we have to say negative 1/3. We've got to make sure you use the right expression. If you don't use the right expression, that's going to be a problem. So make sure you use the right expression. So now we know that we know that the rate is equal to 0.012 molar per second. And we know that we have negative 1/3 times the change in concentration of F2 divided by the change in time. Well, in order to get rid of this 1/3, we must multiply by the inverse of 1/3 on both sides of the negative inverse. So it would be negative 3 over 1. And you multiply, which is, by the way, negative 3. And so you multiply by negative 3. And so now you're left with, these are canceling, they cancel each other out. You're left with just the change in concentration of F2 with regard to the change in time. And that's what we're trying to solve here. Notice that's all we're trying to solve here. And so 0.012 times -3, all right, times -3 is going to be negative 0.036 molar per second. All right, and so does that make sense? Well, is F2 a reactant? Yes, it should be negative. So it's negative 0.036 molar per second. You say, well, that doesn't look like they have the same rate. Well, they do. They have the exact same rate. If you plug this in and you say rate, and you write the rate expression, it's negative 1/3 times negative 0.036 molar per 1 second. What's 1/3 of 0.036? Notice the negative signs cancel, and you're left with 0.012 molar per second. All right, so sure enough, does work out. All right, so you have to just check those things if you want, but you should also note that there's an easier check here. All right, the easier check is look at the stoichiometry, right? This is a coefficient of 1. This is a coefficient of 3. This is 3 times greater in magnitude than that one. And so that makes that a whole lot easier. Okay, so let's go to the next one. And we go to the next one, and all we're doing is the exact same thing, except for now this is a product. All right, which doesn't make it harder or easier. Nothing about it is super difficult. So we know what the rate is. And so I'm just going to use my rate expression just because it's already developed for me. It's a little easier. There's fewer parts. So if I want to say, I want to calculate the change in the concentration of ClF3, change in the concentration of ClF3 with regard to the change in time. All right. And I know that my rate expression is 1/2. All right, 1/2 is equal to rate. So all I have to do is solve for the change in concentration of ClF3 with regard to the change in time. So I'll plug these values in. The rate was 0.012 molar per second. And then here I have 1/2 times the change in concentration of ClF3 with regard to the change in time. And it doesn't really matter where you multiply from. You multiply from here, the inverse of the fraction, which is 2/1 or 2. And so that what that does is that cancels that, and it makes it 1. And you have to do that on both sides. All right. So you multiply this side by 2. And so then what you're left with, and I'm running out of room here, is the change in concentration of ClF3 with regard to the change in time is equal to 0.024 molar per second. And that's it. And does that make sense? Yes, because it is a positive value, and it should be a positive value, 0.024 molar per second. And look at this. The coefficient is 2, and it is twice the value that you saw when the coefficient was 1. All right. And so that makes that really easy to solve. And that's all you're really doing on numbers 1 through 8. You write the rate expressions, and then you're going to be solving for the change of concentration of various components within that equation. And so hopefully that helped. And if you have any questions, please see me. I will be available during this time of asynchronous learning. I have posted it on my page. So anyway, please like and share, and have a great day.